Yeah, so the second talk will be given by my colleague, Professor Saket Saurabh. He works in the area of graph algorithms and parameterized complexity theory. He has several awards and recognitions to his credit. He is recipient of the Swarna Jayanti Fellowship, Santishwaru Bhatnagar Prize, ACM India Early Career Research Award, ERC Starting Grant. He is also a member of Indian Academy of Science, Academia Europea, European Association for Theoretical Computer Science. Saket has been associated with IMSC right from his PhD days. He completed his PhD here in the year 2008. He will talk to us on his kutti PC story.
So it's always very difficult to, speak to such gatherings. So I decided not to speak too much of computer science, but I will have my own share of computer science to this. And if you are not from Tamil Nadu, then kutti means small, and that's what it is. So a lot of, and the PC in this PC is definitely not personal computers, don't worry about it. And the picture here should become clear at the end what it is. Okay, so the principal character will be this object in my talk. So Farheen was saying that, she studied this computer science BTech and she liked graph theory and she moved to some biological networks and everything. I also learned graph theory, but in discrete maths, but we didn't move to, we just started to, for us, the graphs are just nodes, no names, from where it comes, it doesn't matter. And between two vertices, there is an edge, there's a link. What do they represent? It doesn't matter. So we just study abstract objects of graph. So there will be lots of graph. So this is the only definition I wanted to talk about graphs and nothing more. So actually, so what is the plan of the talk? So I'm going to give you like some glimpses of talks with my association with IMSC and viewed through the lens of science and students. And similar in the spirit which Meena said that, that how much we value our graduate students and what. So it is also a tribute to all those people with whom I have crossed my path, whether they were graduate students, postdocs, interns, colleagues. And it's also a tribute to myself because I'm also a graduate student from here. So, okay, so it all started in 99, okay? And when I moved from Hindu college, where I was studying economics, inspired from Amartya Sen, but after 2 weeks, I realized that I like maths more than economics. And that is the time when I was in I think some waiting list in CMI, and I was waiting that if they invite me, I'll go. So then I got a letter that I can go, and this is the place I saw students are turning down IITs for this maths institute, and I know what this institute is. It is the bigger, what is that called? It's a picture of auditorium, outside auditorium in the new place at CMI. So I moved from economics to doing pure mathematics, which is what I liked, but it was not all that easy, okay? But my real story, it did not start at this place or this institute. It started, and also one reason why I actually came is also because it was free education, and they were giving 500 rupees monthly salary, and in those days, trust me, 800 rupees was enough to eat and have some, extra money for every Sunday lunches at Deluxe Hotel in, T Nagar. And so basically, so this is where we started here. This is the J.N. Chetty Road, where the CMI was then. And I was still in early 50s, not in terms of age, in terms of weight. And, okay, and CLRS still did not have S in its title. It was still called CLR. And if you look at H. Venkatesh, who still had black hairs, real ones, then this is the earliest picture that I found of him. It's from 2003 Dakstul workshop. Yeah, so this is the earliest I found. And still, we were in the millennium era, and IMSC was still in the era of ERNET, and I was trying to move from ERNET to RES. So this is my first lecture and of my notebook of 2000, 8 August 2000, of the algorithm lecture that Venkatesh took at CMI. So this is where my association with IMEC started, with an algorithm course, and Venkat is teaching that course at CMI at GN Chetty Road. And so let's move forward. And this is, I was planning to define what should I define NP completeness. So this is what Venkat has defined. I thought, why should I take blame for anything? If this is not clear to all of you what he said, then so it be. Okay? So basically what is NP what is P? Basically all the problems for which you can do polynomial time computation. And what was NP completeness? There are some problems for which you could not solve it in polynomial time. Example, Hamiltonian path. But more importantly, if you look here, n is a prime, you want to test. And we realize that, oh, why? So we all gave this order root n algorithm, try. It cannot have factor more than that. And we tried, but it was not a polynomial time algorithm because it should be polynomial in the encoding length. So when you give n to the computer, you don't give it in 1, 1, 1 n times, you give it in binary, which is log n bits, right? So we were expecting to design an algorithm running time log n to the power big O of 1. And that was still an open problem then. So it was 2000, roughly end of 2000, like November, December, because it's a NP completeness, so it must have come around end. And only the 6 months later or a year later, I remember sitting in this crowd when Arvind was giving a talk on AKS algorithm, and from that S, you will hear more, I think, tomorrow. So that's about NP completeness, the problems for which we cannot design polynomial time algorithm. So it's not my fault that I did not solve primes in P because I didn't get time to solve it. That was a joke. Okay, and so as it is standard in, hardness means nothing. So these are some of the things which Venkatesh tried to teach us in last 2 lectures of his algorithm course. And so he taught us approximation of them as a mechanism to cope with NP hardness. I will define one of these 2 things in a few slides. And he also used the word parameterized complexity, which I will define in a minute a bit more. So we learned about NP completeness in this course. We learned about how to cope up with NP hardness. And then, so the PC in this title actually stands for this parameterized complexity, which was the last thing that Venkatesh taught in the class, which has stayed with me for last 2 decades. So this is an algorithm for Vertex cover that he gave in the last lecture. Okay. So let me tell you what is the mantra of coping with NP hardness is. Okay. So basically this is what I always tell, that basically NP hardness is, there is no algorithm for this problem that solves all instances optimally in polynomial time. Okay. And now, so what is coping will mean is that let's relax each of these definitions and see what we can achieve or what we can get from there. So all instances, maybe just forget about all instances, maybe just look at some restricted input. Maybe you don't look at all the graphs, maybe look at the graphs that are embeddable on planes or embeddable on graphs of genus 2 or whatever. Or just look at trees. And this is also a motive of parameterized algorithms that I will define in a minute. But there's also a big branch of computer science where we forget about solving it exactly and say, hey, we still give you polynomial time. We are happy if you give us some approximation, but that approximation should be guaranteed. If you tell me that if the optimum has 10, then I will give you 20, but you should be guaranteed to give me always 20 or factor 2 approximation on every instance. So these are like guaranteed approximation algorithm, but running in polynomial time. Or you can just forget about this polynomial time and say, hey, let me allow you some more time. Can you still do much better than the naive search, which I will get in a minute. And there's also a notion of kernelization that I will not go about, which allows us to solve a bit more what you can do in polynomial time. Okay, so here's my vertex cover problem, which is very central problem that I must tell to the audience. You're given a graph G integer k, and you have to ask a question, is there a vertex at S such that if I delete these endpoints or the vertices, there is no S left. So what does it allow is it? So what is the motivation? So I know that in computational biology, people model this vertex cover for like some interactions which they do not want or something. And there has been a lot of, bioinformatics work has been done on this. So basically, this can model if you wanted to resolve conflicts and things like that. So this is a basic problem which has lots of motivation. But like for us, this is a basic problem that we learn in, like, this is a baby NP-complete problem in my head. Okay. And so alternate view is you want to remove k vertices, you want to remove such that there is no connections in your graph. Okay. So there is, of course, there's an algorithm for this problem, right? You try all subsets and check. But if you're only interested in checking of size k, then why do you have to check everything? You just check all subsets of size k and you will be happy. But look at this. Like if all subsets, all k subsets of VG is so much more. But if you want, what is the main mantra or main idea is that I do not want to search over all n choose k. Can I search smaller amount of space? Like only a small number of this n choose k and still answer. So of course, the ideal will be that we only search polynomial, but these are NP hard problem. So the hoping that we can do this is not possible. So we try to say that, okay, look, it's just still polynomial, but I allow you some function of some objects, like k being the size of the solution that I'm looking for, on this number of subsets that you're allowed to look for your solution, okay? And so that is the whole idea about parameterized complexity that starts. So what is parameterized algorithms? So we often assume that this k that we are looking for is reasonably small compared to the input size. So think of like n as like 1,000 and k is like 20. And then this n to the power k is way too slow. I mean, you cannot do this. But the idea is, can we narrow down this search space from this n to the power k to something smaller, something better? Okay? And this is an algorithm which does this for vertex cover. So what did this algorithm tells? Hey, here is an edge. You told me that you have to pick one of these endpoints. So you pick one of these, delete it, check whether the graph has a vertex cover of size k minus 1, pick this, delete it, check with the graph has a vertex cover of size k minus 1. In both sides, we are looking for a vertex cover of one less size. So that's just your recursive algorithm. And if you write down the recurrence, this is what we wrote, this solves to some 2 power k times m. So that's your vertex cover algorithm from my undergraduate algorithm course. Okay, so that was an FPT algorithm for vertex cover. So what is the mantra that we try to do is that n to the power k plus 2 is polynomial for every k. So if I put k equal to 3, it is polynomial. K equal to 5, it is polynomial. But versus what we want is same polynomial for every k. So like now if you look at this is the algorithm, if you put k equal to 100, still linear. Of course, the constants are very bad, right? But this is what we mean by fixed parameter tractable, that with respect to input size are still very good, just same as polynomial, but with respect to some parameter or something, you're allowed to be exponential or you're allowed to be unbounded. Okay, so this is bad, this is good, okay? But let me quote David Johnson here. So these kind of algorithms also follows from, for many, many, many problems, those are the only known polynomial time algorithms that follows from the like big, deep theory of graph minors of Robertson and Seymour, who's like some 600 pages from 86 to 2002. Those constants are like just horrible. They're not even computable, right? So compared to those constants, if you have n to the power 100 of them, that is much better. That's all that he's trying to say. So the theory of designing such algorithms has always been there, like early 60s, 70s, 80s. People have done it for linear program. People have done for integer linear program. It's just that what was missing in the theory is that, hey, when you cannot do this, right? Like when for a problem, you cannot design such an algorithm. And that is what is the contribution of parameterized complexity or the field in itself is. Okay, so these are basic questions that we ask. Is it FPT? Is it f of k this? Can we do better? Smaller f of k, smaller n to the power c at the same time. So these are the kind of questions that we try to address for different problems, various problems, and see what we can do or we can achieve. Okay, so now I've given you some little bit of definitions. Now it's time for me to go back And in the summer of 2001, like as always, being in CMI, what you will do, like you see everybody is going for some internship, so you also write for internship. So I came to Venkatesh and said, hey, can I do internship with you? He said, sure. And in one of those huts, he gave me this problem. It was still hut in the old days, which was burnt later. But, so graph G, integer K, does there exist a vertex set S such that the following happens? G minus S has no cycles, okay? So this is why it's called feedback vertex set. And we want to find a smallest size of size at most K. So here's a graph, okay? Look, if I delete A, there is no cycle in the graph. And cycle just means you start from one place, you go around, you can come back to yourself, okay? So basically, in the language of graph theory, it is a forest. So this is the first question that I have got, and I have still from last 20 years, some way or other, all my students or myself, we have done something about this for either an undirected graph, directed graph, subset version, modular version, whatever version you can think of. So this is the question which I got in 2001 in the summer, and it is NP complete. Nothing happened for next 1 year, like nothing. Like I tried, all I did is that I went to the board, draw n to the power k, draw some circle, I wrote n choose k, but that's all that I did on the paper. No progress, nothing happened. And then in summer of 2002, like early part of May, I went to Venkatesh and said, hey, nothing is happening, can you change my problem? And he was going somewhere on that, it was Thursday or Friday, he turns around and he says, this is what I attribute to him, is that research is a trade-off between breadth first search, this is in computer science, and depth first search. So just do something for this week. When I come back from my trip, I will give you some other problem to work on. I said, okay, fine. 1 more week and then something will change. And then, in that 1 week is this is the first result that we showed, and which basically says, you look at a graph G, either it has a cycle of length 12, or you need lots of vertices to hit all the cycles in the graph. Either they just small cycle or this. And this also has a nice story. And the story is, I don't know whether you know him. His name is Amitava Bhattacharya. He's I think, maths faculty at TFR. So at time, I was given this flatlets, and he was my flat mate. And K.R. Parthisathi was here. He was giving us lectures on quantum algorithms, and he was scribing those lecture notes on quantum algorithms. So I never thought that he will have interest in graph theory and all this. So one day I went back, I said, he asked me, what do you do? So I told him, I do graph theory and more. Oh, I also have interest in graph theory. So what do you work on? So I explained him everything. And then he told me, oh, why don't you go and read this Erdos-Poza theorem, which basically says that every graph either has k vertex disjoint cycles, or it has some k log k vertices that intersects all this. And so I told him, I don't know. I don't know from where he read it. And the next evening, he actually gave me the proof of that. And using those ideas, I was able to show this. So this is how my first research started. So thanks to Amitava. 2002 is also special because I met my wife in CMI. And so if you look at the title of her talk was Matching Under Preferences, Stability to Popularity. Now, it was matching under preferences, whether it is stable or popular, you have to go and ask her, not me. So that was my first result. And I don't know what happened, but I know that we proved this. CRS and Venkatesh used to stay in the same place in Lilavati. Next day, I saw this paper written. I have not typed a single word in this paper, but it was typed, done because I was going to my hometown for some reason. And it was written, submitted, then, so like I have no clue, but that's all. But I know that that result played a very central role in this. So this is my first paper, which came about thanks to CRS and Venkatesh, who did all the job in this. In 2005, I came across, so when I was by that time, I was a PhD student in IMSc. So I came across a problem which I really liked. It's called dominating set. So it is same like graph problem, but now you want to find a small set of vertices such that every vertex either belongs to this set or someone has a neighbor in it or has a connection in it. So that's what is the definition of dominating set means. So for example, look at A. Every vertex has one edge incident to A. So A is a dominating set in the graph. Of course, this problem is NP-complete. And then I came across this habilitation thesis of some colleagues of ours in West, which said that, oh, dominating set can be solved in time root 3 to the power k on bipartite graph. And proof was not there, so I thought, oh, he's mentioning as a corollary to whatever I did, it must be something very easy. But like, we tried, nothing happened actually. But what we proved, like what's the reality is. So what we managed to show that, hey, forget about this root 3 to the power k algorithm. You cannot even have an algorithm with running time f of k into the power little of k, unless, of course, some bad things happen. For example, we are able to make cold fusion tomorrow, for example. Right? So like, right? But the point what I was wanting to mention is that, but this told us something very interesting. So while I was trying to show this, recover this proof, I did have a proof that it has a good algorithm, but not on the class he was trying to tell us, but something we told, oh, so it's a 4 cycles in the graph that were the trouble. So if graphs do not have these 4 cycles, things are good. So this random discovery, because we were trying to prove someone's wrong algorithm, was a great motivation. And this paper was the first of its kind in its time to do, like study these kind of problems with if a subgraph is missing and this and that, which has led to a lot of development later. And I will mention this after some time. Okay, so this is my only, probably last technical slide, which I told to some people that I will tell you one missing piece, which I have always not told. So let me tell you so this is my foray into ETH and Seth. So if you do not understand this one slide, please bear with me. So this is an NP completeness reduction from 3 SAT to K vertex cover that we teach in our class, okay? So how did it came about? I think I was talking to Nitin Saurabh in one of those classes, and he said, this is very interesting, because I was teaching also kernelization to them, and he just said, this looks very interesting. In like few months back, this has small tree width, okay? It went past. But later, this gadget actually is a starting point for all these reductions that you see in parameterized complexity and many p-time reduction is the following. You don't start with 3 SAT, you start with SAT. Then these 3 guys will become a clique, okay? Now if you delete these 2n vertices, it is disjoint union of cliques. So what is the tree width of this graph? Is 3n. That implies if SAT cannot have 2 power n algorithm, then you cannot have 2 to the power tree width by 3 algorithm for tree width, vertex cover parameterized by tree width. Of course, once you have one result, you push it, right? So basically what we did, but this is a starting point of lots and lots of results that happens. This just simple observation that if we replace this 3 with clique, it is something interesting that can be employed with. So that was my last technical slide. Okay, so we are done with NP completeness, coping with NP completeness, parameterized algorithms, restricted input, editing graph. So one thing that has been central to lots of problems is what is called editing graph. So basically, if you notice the kind of problems that we have considered, is that you're given a graph G, you're given a graph class or property pi, you basically want to do some operation like deletion, vertex deletion, edge addition, edge contraction, edge editing to get to some particular graph class. For example, vertex deletion, edgeless graph is a vertex cover. Feedback vertex set is an acyclic graph. Edge addition is what is known as minimum fill-in. So basically, you're given a graph G, you want to add edges so that it becomes what is known as caudal graph, okay? And this is also a lot of application in Gaussian elimination and those networks. And edge editing, like you want to maybe delete some edges, add some edges to get a bunch of clicks, okay? And there's also a big theory, what they call mix them up. And there's a notion of minors. So what is minors? So if for me, giving a talk without minors is a bit, so here it is. So you're given a graph G and H. So what is a minor of G? If you can get H from G by following operation. If you want, you can delete vertices. If you want to delete edges, you delete edges. And if you want to contract edges, you contract edges. So if you can get your graph H starting with G, then this is called minor. So you can show to yourself that like if you have a planar graph, you cannot get a complete graph on 5 vertices by doing any of these operations. Or a complete bipartite graph from 3 and 3 vertices, you cannot get this by doing any of these operations. So they are very powerful. Probably, if I have to say, this is single most important object in modern graph theory and algorithms. And again, it comes from Robertson and Seymour. Okay? So this monster 600-page proof has many, many such algorithmic insights that people have used time and again. Okay, so now it's time. So these are the set of topics, and the people who have done PhD about take the graph, edit, do something, are here the set of people. Like here's Philip, who did this dominating set and did many more things with dominating set. His Fahad, he also did lots of graph editing, but he was very much interested in randomness, linear algebra. So he started to use tools from these objects in graph algorithms. Neil, who actually, we proved some very beautiful theorems, like which problem can have polynomial time preprocessing, like very large fraction of problem, which still remains the state of art for now. And MSR, he was a very bright guy. So he was doing master thesis with me, and I gave him a problem. He said, hey, I want to work on something. So I gave him something which I had tried, and I didn't believe that he will do it. So in the afternoon, he comes and says, hey, I have a solution to this problem. And I was like, okay, it will take me some 5-10 minutes to just get rid of him. So, but he starts to explain the proof. Of course, there was a bug, but it was not that fatal bug that we cannot fix it in another 2 hours. So he actually started working on something on cuts and flows, augmenting paths, and he has mastered that art, and he's at University of Warwick at this point of time. Ashutosh also did on lots of graph editing problem. Parnavendu, he came and he said, he was from CMI, he said, oh, don't give me freedom for 1 year, I will come back to after 1 year if I don't do anything. So he wanted to do some random linear algebra, this. So after 1 year, he came back. We did not make progress in what we were trying, but he had learned enough mathematics to apply tools from algebraic geometry, this computational algebraic geometry to his work. So a lot of this part, like Wronskian matrices and this, it is his given in the lot of works that we did in those graph editing problems. Okay? Akanksha did also on polynomial time preprocessing. Prateek liked edge contraction, so he's still doing edge contraction for last 7-8 years. And then there were Lockwayne, Abhishek, Rohani, Jay Kristen. They did different versions of many of these things, and they are at different places at this point of time. And there were other people who did not want to do work on graph. They were very clear. So you will hear the talk from Sudeshna. She wanted to apply the idea of parameterized complexity, but she has roots from ISI, so she was always interested in computational geometry. So she did computational geometry with us. Misam, he had a physics background from IIT Kanpur, so he was interested in linear algebra. And Sanjukta had an interest in computational social choice, like game theory and this thing. So she did PhD in these topics, but from the mantra that we have to design such kind of algorithms. Okay, and I also was fortunate to have some amazing postdocs like Manu, Pradisha, Bart, and then some Mera, who's in Ben Gurion, William, Pallavi, Kritika, and then I have current set of graduate students who are pushing these boundaries in different fields, and then I have current set of postdocs who are doing all this, and the circus goes on. And not only this, I just gave you a very glimpse of this. We contributed much more, like to many more substrata of parameterized complexity, graph algorithms, like you name it. You will find that we have made some contribution to most of those areas. Okay, and if you want to know more, here are 2 books. You can, and now you see, this is basically a book. So basically, it tells us that what is this? If you take a planar graph, what is the big grid that you can get by contracting these vertices, right? So it has a relation to algorithm. So this is where the picture comes from. And let me thank all the funding agencies, like be it DST, DAE, ERC, and of course IMSU, who has hosted whole lot of dignitaries and visitors. So thanks to all of them. And that's the end of my story. But before I end, here it was 18th December 2022. We had this amazing get-together when most of these people were there for FSC thesis, which happened at IIT Madras. So we had a big dinner at one of those days. So it's a picture from those. And this is the most, fulfilling thing to see students and their students in this lab. Thank you very much.